or what are the algorithms that are available and what are the terms and terminology of the RL. So we'll try to look into that and it's just a bird's eye view of that. So it's not that we are covering most of the RL parts, but we are just going through the over the top view of the different concepts that are there.
Hmm.
So we require to familiar with these things in the initial part. Okay.
Okay. Okay.
Okay. And we'll start. So, in the last class, I think we have already discussed about mm, all these slides, right? So, intro to RL and how exactly RL differs with the supervised learning and what are the problems we can solve using RL and how we can calculate RL for MDPs and SMDPs and how we can define this agent environment boundaries. MDP property, Markov property, defining the state actions. This point. Yeah, we have discussed Bellman equations, optimal functions, backup diagram.
Backup
Yeah,
diagram we didn't discuss. Right?
yeah. So this backup diagram is nothing but as I was drawing the nodes regarding the state and actions of state transitions. So there is calling it as a backup diagram. They are drawing it in the different. So you are able to see my screen, right?
Right. Right.
Yeah. So if you
Uh,
see this v pi, they are just telling the relation between this v pi of s and q pi of s. So this is nothing but your action value function, and this is your state action value function. So that is the difference. So here we'll be having that action term of the involvement. And if you see this VPI also, this is but your policy evaluation. So there are two things. One is the policy evaluation, and one more is deriving the policy itself. So in policy evaluation, given a policy, taking a policy lead and we discuss that finding an optimal policy is the final goal or final aim of the MDP, solving the MDP or solving the RL problem, right? So come to the policy itself. So you have two things. One thing is yeah. So first step is evaluating policy. In this, what happens is you have given a policy, some arbitrary policy is given, and what you will do using this policy, you will evaluate your Q conditions or your expected and then you will try to see or make comparison between these two equal to true star or not. Or what is this Q value is. So we'll just do our policy evaluation. Let's given a policy. And deriving the policy is nothing but we'll try to find an optimal policy. So we will try to explore different set of actions with respect to the state of the transitions and given or it is optional. So transition probability is nothing but so given all this, we have to find a policy, and you have to use some algorithm iteratively and flash in such a way that this policy converges to what finally you will get an optimal policy. Again, there are some set of algorithms in doing that. So these are the two differences. One is policy evaluation, and one thing is deriving the policy from scratch. So these are the two
can you
things.
repeat it? It's not clear.
So in evaluating policy, you are given a policy. So already a policy is given, some arbitrary policy.
Okay.
Okay. This policy you are evaluating and trying to see what will be the Q value for this particular policy or what is the value function for this
Okay.
Okay, and then after getting the value function, we can just compare it like is q whatever the value function is the optimal value function or not, or what is the behavior of the q value or something. We are just evaluating a given policy. Somebody have gave you a policy, you are evaluating the policy.
Okay.
Okay, is it okay?
Okay. Uh, Policy in the sense one state to another state or the whole thing?
Complete thing. So policy
Okay.
means what we have discussed. It is a
Right,
tree
right.
which have
Okay.
state to action columns, right? Where you are in some state S1 needs to take action, and then state S2 needs to take action A2. So we have all this table.
Okay,
It is
okay.
nothing but your policy.
Mm-hmm.
So somebody has given you some policy already. This type of policy they have given. So you
Okay.
are evaluating this policy,
Okay.
okay, to get the corresponding value Q function and state transition. So we are just evaluating this. We are doing it.
In
And
the
then second,
policies, we don't have the rewards. Like if we take the state, this state action, and this will be the reward. That is not mentioned in the policy.
no, the reward is not there.
Okay. In the value function, we calculate the reward also. Like,
No. See, as of now, you just take like policies, but you have stated action.
mhm.
So it's based on your reward again.
Okay.
Based on your reward only, you will choose the action, right?
Then why are we again evaluating it? Because we have already done it, right?
No. It is like we have given some arbitrary policy. So we have some arbitrary policy.
Okay.
So you don't know this policy is optimal or not.
Okay.
Suppose this is your policy.
Hmm.
Okay. So this is your policy. Fine.
Okay.
Okay. When your policy will be called 5 star optimal policy.
When it is the best. But how will we know it is the best? This is unsupervised, right?
How will you know it is best is it will become best when you are choosing in S1 when you are choosing action, whatever action, which is giving you maximum power faster.
Okay. So it is same like deriving policy also. Deriving policy also is doing the same thing. It's also
No, see, this is other part. So I'm just telling you so
okay.
that you will understand. So this is nothing but evaluating policy. But somebody has given you some policy, some arbitrary
Mhm.
policy is not make you some arbitrary reward.
Okay.
Okay. So somebody have given you policy. Your job is to just take this policy and perform this state action. You will perform this state this one when you are in this one perform given action. You will get some reward as well. And then you will get some S2. S2 you will do some later action. What you would like to do. And at the end you will calculate the total
Okay. Afterwards,
and take it. And keep it somewhere.
that's
This is
it.
evaluating policy.
Okay. We don't care about our R star or whatever.
Is it optimal or
Uh,
not? We don't care about that.
oh, okay. 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 Just running it.
Evaluating means somebody has given policy or finally calculating
Achha,
what is
just calculating. Evaluating means I thought that it is trying to find that this is wrong. This is itna kami hai isme kind of.
no,
Okay.
no. Evaluating is nothing but calculating.
Okay.
So
Okay.
it is
Fine.
just a calculation. What are the total reward.
Okay.
Okay. And then coming to deriving policy is nothing but you don't have anything. Means
Hmm.
you don't have policy or you don't have optimal policy or you don't have any policy.
Right.
You
Right.
don't have see, yeah, don't. But you are trying to find a policy, a
Correct.
type of policy.
Hmm.
Suppose if you want to find optimal policy, in
Hmm.
our case, generally that is called the expression. So if you want the optimal policy, then you have to start somewhere, right?
Hmm. Hmm.
Either you will make an assumption on policy side, or you will make an assumption of on um, value function side, q value side. Somewhere you have to start. So either you will start with some arbitrary policy, or and then slowly improve this policy, or either you will start with taking some q values and then backwardly deriving some set of policy which will give you maximum q value.
Hmm.
So based on the algorithm we are using, we will just start somewhere and then we will improve upon, and finally we will derive one policy. That policy will be your optimal policy.
Hmm.
That means for every state action pair, for every state action pair, you are getting maximum reward. Or finally, whatever the reward that is going to obtain on the two value that you are going to obtain, it is the optimal one. That is optimal value.
Okay.
Okay, this is the difference between deriving policy and evaluating policy. And then if you go back, going back. So this is nothing but your policy evaluation stage.
Okay.
This one. So here what you are doing, given a policy, suppose you have a policy. Policy means what? Given a particular state, what action you have to take.
Hmm.
So you have your policy and you are evaluating your policy. And finally you are calculating your B5 of this. So that is one thing. And then this is again like without giving the policy, you want to calculate the reward, whatever the key value is there, you want to calculate. How you will do that? As we were discussing in the Bellman update keys and many times we were
Hmm.
discussing that this is nothing but your immediate reward plus discounted factor into your VPI of S.
Hmm.
But
Future.
here we have this problem also because we have the state transition problem, whatever we were discussing. So because of all this, we are getting this equation or this updation we are doing
Hmm.
for getting your Q value,
Okay.
for updating your Q. Okay. And then yeah, and then you have this VPI of S, and then if you see, if you are making some state to state transition or something, then you are taking some action and you are receiving this reward R, and then you are getting a new value function VPI S dash at this state S dash.
Value
So
function
this is the
and
definition, and
value function and Q function are same or what?
yeah, value function and Q function are similar. So they
Okay.
both are the average expected reward only.
Fine.
But in Q function, you will have the state and action pair.
State and
But in
action
value
pair.
function, you only have state. If you
Okay.
see here,
Acha. Uh,
you can see it. Right? This have
uh,
only S. This have
okay. Value function.
you have this, and yeah, this is again it's a combination of whatever the policy evaluation we are doing and updation. So you have a policy here, given a particular policy, and then you are calculating the average expected reward of the particular state transition. So if you are moving from one state to one more state, what is the reward you are going to get? And for that policy, for that particular given policy, what is the reward you are going to get? So finally, you are calculating your reply of this. So repay of S is nothing but given a policy by what is the value function of the particular policy.
In value, we don't have action.
You have the action. So A belongs to A, right? So we have,
Okay.
see,
Q
suppose
doesn't has action.
somebody has given me,
Okay.
what?
Uh, you said that Q as state and action pair.
Yeah.
Okay. So value doesn't has action. So
See, yeah, see, as of now, you take that Q or B or whatever the reward we are speaking, everything is same. So you
okay.
just take it as whatever the value function we are discussing, your reward, total reward,
Okay. Okay.
total expected reward.
Hmm.
Okay. That will be better for you for the next time.
Okay.
So this is your reward. So what you're doing, given a policy, so you have given some policy and you have to find the total reward. So what you will do, We'll just take, suppose you are in some status, then what you will do, given a policy, what is the action you have to take? So you are in status. You'll look up in the policy like it action, then you will take that action. That is nothing but your means your action. After taking action, you will get some observation or you will get some reward. So you will take this reward, and this is the discount factor for that reward also. So this is a complete reward. This is long-term reward, and this is immediate reward. This is the total reward. So with respect to your policy and the reward you are obtaining, by doing a summation of this for all the actions, we are finally calculating your value function for that particular policy, given policy.
Why are we summation of all actions? Like for one S to the another S, we'll only do one action, right? We'll not do all actions.
That depends on the policy.
Uh,
Yeah. See, one thing is, again, it depends on the type of policy. Take a fixed policy, deterministic policy, stochastic policy. In deterministic policy, what happens? This policy will tell that, here you have two things. Deterministic policy. Here, what it will tell is, you have some state. If you are in state S1, you take action. If you are in state S2, you take action. It will tell only this. But if it is a stochastic policy, then what it will tell is that if you are in S2, this action A, 30% probability. Suppose if you are in, take A2 with 30% probability, A3 with 40% probability. So in this case, in the first episode, you may land up with this action A, but in the second time when you're running the same policy, you may land up with this action also.
hmm.
So that is the reason I told it is, it depends on the policy. And then you are making this transition, right? S1, S2, S3. So whatever the transitions you are making, these transitions you have to find the value functions, right? So this is nothing but your final value function is nothing. It's a summation of all these value functions. So this is nothing but your immediate reward R plus gamma into whatever the probability or transition state transition, the reward you are going to have. They are showing.
But I'm thinking more naively. Like, for example, if we are in first floor, okay, that is one state, and we want to go to the ground floor. That is the another state. So we have two actions: get down or get up. So we'll always choose get down, right? Why we'll go for get down and get up? We'll do both and sum that probability. We can choose only one
No,
action, right?
if you are deterministic, if you are in this case, then you will tell that you will go only to one. Every time you execute the policy, you have to only go down. But there are some cases where you have to make a trade-off, or you have to choose in such a way that every time you cannot be deterministic. Right? Obviously, we are dealing with a real-time system. There is a stochasticity that is involved. So that is the reason. Instead of telling that 100% you go take this action, we'll tell that you action with this much probability, and you will take this action with this much probability. So
That
based
is
on the probabilistic, your actions will be also probabilistic.
that is fine, but still we'll do one time. What we can do is S1 A1 we can do once, then S1 A2 we can do once. How are we clubbing both of these things? I'm not understanding that.
That is what. See, if you are fixed, then you can just tell that. See, one thing is, when you are in a particular state, you can take only one action. Right? It is not that
Ah,
A1 and A2 both.
exactly.
You cannot change also. So you
Right.
have to take only one.
Ah,
So when you are taking it, either you can take it 100% probability, only this every time.
okay.
So even if you execute the policy 100 times also, and when you are in state S1, you will go S2, to action A1 only,
Huh.
right? But in the stochastic case, what happens? It is doing with some probability, right? So what happens if you are suppose say if you are running this policy for 10 episodes, then what happens in past episode in total 10 episodes, three times it will take for the same state S1, it will take action A1. For same state S1, three times it will take action A. Four times it will take action A. So same state to state transition only. But when you are doing that, the action it is taking is going to differ. Why? Because this is probabilistic.
Okay.
Okay. Why we are
So
going optimistic because again it depends on the if reward also stochastic, then obviously the actions you are choosing also should be stochastic, and there are many set of things that are also why we are choosing the stochastic policy to ask a direct question.
so how will we like backtrack? Like which one was the best? A1 was the best, A2 is the best, A3 is the best. Because we are summing all the up, then how can we just differ that which one was the best?
Best is nothing but that's not the if you have a database, if you are very much from that, if you are 100% sure.
Mm-hmm.
So then what you can do, you can just take the deterministic policy and it will be true that for every S1 it will be. But when there is a case that the action you are taking itself is not sure. If you suppose if you don't know the rewards also, you don't know the state transition probabilities also, then you don't know what will happen. Right? If it is not 100% sure that every time you want to take this action. So you may have to sort of move to some other action also will be probabilistic. So it is.
Hello?
So that is the reason.
We can't hear you. Hello?
Uh, Hello.
Your
Am I
voice is
audible?
cutting.
Now is it okay?
No, it's fine. Uh, the only question I wanted to ask that it is fine. I understood that it is probabilistic. It can be A1, A2, A3. That's fine. But what we can do is we can first what we do S1, A1. We'll find the value function. Then what we'll do next step S1, A2. We'll find the what is the value function. Then what we can do S1, A3. Then we'll find the value function. Whichever is the greatest, we'll choose that. Why are we summing all the actions into one equation? That I'm not getting.
See, that is the case when suppose when A1 when you are going for A1, it is giving the same reward. Every time when you choose A1, you have some fixed reward. When you choose A2, you are getting some fixed reward. So if you have a fixed reward concept, then what you told is true. We can do like. But suppose reward itself is probabilistic for stochastic. So you don't know when you choose A1, you will with some probability you will get this reward. Then what you will do in that case?
Mhm. Okay.
You don't know, right? So
Mm.
in that cases, you will do stochastic.
Okay.
Yeah, and then coming to the valuation part, and regarding the optimal policy we were discussing, right? For any Markov decision process, there exists an optimal policy phi square that is better than or equal to all other policies. So yeah, so our aim is to finally find this optimal policy,
Yeah.
and this optimal policy will give you the optimal d phi of this value function. And yeah, obviously. So if you have a pi which is greater than pi dash is nothing, but you are getting a v pi which is greater than v pi dash. That's correct.
Mm.
All optimal policies achieve the optimal value function. That is also right. Right? So if it is optimal policy, means if it is giving optimal value function, then only if it is giving the optimal reward value, then only we'll tell that it's optimal policy.
Right.
All optimal policies achieve the optimal action value function. Right.
Mm.
So you will get a for optimal whatever the policy you will get the optimal value function. or expected reward or something like that. The reward term is there, we will get it as maximum, or that is the maximum possibility that can get for the particular individual. Okay, right?
Yeah.
So how to get now? This is the important question. How to get optimal policy. So finally, we understood that our aim is to find the optimal policy. So now we have to think of how can what are the algorithms we can apply or how we can find the optimal policy. So, optimal policy can be found by maximizing over Q star S of S comma A. It is nothing but, as you told, how you can find our policy means if A equal to R max of Q star of S of A. It is nothing but, suppose you have taken this set of actions. Suppose you have some for S1, you have some S1, and you have some and what you are doing, you are calculating the Q process. And then you are making a argmax of this argmax of whatever the queue is there of the queue values. So here what you are doing finally whatever the maximum value is there of this code we are trying to get right.
Hmm.
So that's what they are also telling. Can be found by maximizing over the Q of S of S. So if you find the argmax of it, then you will find you will get what is your optimal policy. Yeah, there is always a deterministic optimal policy for MDET. If you know QSA, we immediately have the optimal policy. So our aim is to finally find that particular Q star SC. So if you find value function, so there are two things. Either you can find the optimal either you can find the optimal value function and then plug that into a policy, and then you will get your optimal policy, or you derive an optimal policy directly, and then calculate the optimal policy whatever the value, then that should be optimal. So either ways you can do it. Some value function also you can take some value function, arbitrary value function. Slowly you can into it, and finally reach the maximum value function. Restart. Then if you see what means which policy you are getting to restart, then you will get your whatever the optimal policy is there. That will be your optimal policy. Or what you can do is you will start with an arbitrary policy, then you will improve the policy a bit, and then slowly you improve it. Finally, you make it as the optimal policy. Then, as it is optimal policy, obviously it will yield the optimal value. So we can find the optimal policy either way.
Mhm. Right.
So these two are called policy iteration and value iteration in the terminology. Then there are again sort of like comparisons and discussions regarding which one is the best one. Should we have to go with policy iteration or should we go with value iteration? Which one converges faster? This kind of things are there. So both have its own advantages and disadvantages. That is the reason that something called this anchor-centric algorithms where they are using either of them. So both of them they are using. That is the reason they are taking advantages of both the concepts and they
Both.
are building it. Many algorithms are built on top of this concept.
How can we use both?
That I'll tell you when we go to the actor first, and I'll tell you how they are using. So they are defining the actor and the critic, two different parts. So one is doing the value iteration part, and one will do the policy iteration part. And after some batch updation or after some batches, this will update the value function into the policy.
But it will contradict. There can be a contradiction also, right? Policy has different something and value has different. Then it will contradict.
No, no, it is not like that. You are just finding the value of value. So whatever, suppose your actor is there, it will calculate the policies, and whatever the critic is there, it will calculate the value function, and after some set of updates, it will just give the value function. or equal this value into the policy, whatever it is deriving, and which will help this policy to identify or correct its whatever the policy updation it is doing. So like that, both will complement each other, and finally they will arrive to a optimal policy.
A policy at last is derived from value only, right? No?
We can. It is not like that every time. So you can just choose some gradient descent kind of the policy gradient. That is what, so there is some algorithms called policy gradient which compilers where you will directly formulate the gradient of the policy, and then you will slowly try to you will start from with some arbitrary policy, and slowly you will move on with the gradient updates. So slowly we move on to the optimal policy directly.
How can we have gradient over here if we don't know the optimal policy?
You don't know the optimal policy, but you can reach it. So it's like
How?
a deep learning problem itself. You have some loss function. If your objective is to find the minimum,
But
see our
uh, we have the actual value, right? For example, if we have predicted
we have
5,
the loss.
uh, so in linear regression in simple, if the actual value is 10 and we predicted 5, so we can have the what we say loss mean square and do the gradient descent. But here we don't know the actual value, right? We don't know the actual path.
It is a supervised learning setup.
Yeah,
So in
so
this learning setup, you are using a foundational logic, and then you are applying some iterative optimization method or algorithm for doing that. So
right.
if you can formulate the same problem in a supervised setup, then we can use the same gradient descent setup for
How?
doing that.
No, no, we cannot because we don't have the actual value, right?
No. We may not have the actual value, but we may be having, again, there are different kind of what we say, different algorithms or different methods using which we can do the sampling updates. So one thing is using dynamic programming, we can get the sample batch updates immediately. And there is something called Monte Carlo regression. There is TD learning. So again, there are many things using which you can do that.
It
So
doesn't make.
you may not have the actual value,
Uh,
but you may take invention of the value, or you can
Acha.
take a target value and implement it in that. So again,
Uh,
there are different things. So we'll
Acha.
go through that slowly.
Uh-huh. Okay. Okay.
So as of now, you take it as we have to find this optimal action value. For finding that, we can use this equation and we can find the optimal value. And then how we can solve this transformation process. We have to find the so prediction is nothing but for a given policy estimate value functions of state and action takes. So this is nothing but the policy evaluation which we spoke of.
Hmm.
And then control is nothing but estimate the value function of state and state action pairs for the optimal policy. So we have to estimate the value function for the optimal policy. This is a control part. So whatever we have discussed in this,
Hmm.
and then solving the Bellman optimality equation. Again, if when you are formulating it as a MCP, so the main difference between MCP and RL is in RL when you take model free case, so we will come to that later. So for solving the Bellman optimality equation, there are some conditions. It is nothing but you should know the accurate dynamics of the environment. Dynamics of environment is compulsory, or you have to include. And we should have this computational constraints towards space and time constraint. And whatever the problem we are solving, it should obey this Markov property.
What is that?
So if these are there, you can,
What
yeah,
what
then you can
what is the Markov property?
Markov property we have discussed it, right? Whatever the future state is there, it is only depending
Okay.
on the present
Present
state.
state. Yeah, yeah.
It is not depending on the past values.
Past was,
We are
right, right.
assuming that whatever the past information is there, all that information is present in your present value itself.
So isn't this a very big thing?
Yeah, see, if you see a stochastic process itself,
Hmm.
there are some set of processes like non-Markov process and Markov process.
Right,
So
right,
it is very important. We are only dealing with some kind of stochastic processes
uh-huh,
or a decision process which is obeying some property. That is
right,
only a
right.
Markov process.
Okay, okay.
So see, again, there are some set of theorems and algorithms in this. So if you see, there is something called Bellman gap multiplication. So theorems are there. So which prove that when it is Markov, then only we can um, bring this concept of dynamic programming and Markov
Acha.
addition process and then do this. So it's very important that it obeys the Markov property.
Okay.
Okay. And when you take Bayesian graphical models also, so this is a graphic, we discussed about the Markov case, right?
Right.
So
For discrete.
what is this Markov model, and what is a hidden Markov model, and how exactly this Markov case will be propagated. So all the things we have discussed, right? That is the reason we have discussed that.
Hmm.
That is important concept to discuss things about that. Mhm.
Markov chain is just for discrete random values, right?
Yeah, yeah, it is for discrete.
Uh,
That is again a chain. We do
okay.
discrete transition.
Right, right, right.
Yeah, P is nothing but your dynamics of the model or transition probability. That is here. Right?
Yeah.
And coming to this is the one what is it important diagram which you just take a note of or just see this and
Uh-huh.
there are many things here which you have to understand. So there are something called value function based inference. So we have discussed it, right? Like
Hmm.
what is a value function and how we can get optimal policy in value function. There are something called policy based. So in policy based, using stochastic gradient descent directly on discounted expected return with policy function. So as I told, right, everything is a gradient descent and then we can find the optimal policy. So there is this kind of algorithms that are available. And here what happens is you will select some action and according to value function or some Bellman you will update your value function. So here what you'll do, you start with some arbitrary value function and slowly you will improve your value function and finally reach some optimal value. Here what you'll do, here with some arbitrary policy you will start and slowly you will improve your policy and reach your policy 5 star. So these are
Both,
two different.
both like are mostly same, it seems.
No. These are different, right? Because here you are improving your policy. Here you are improving your value.
Uh,
So from value you can derive policy. From policy you can derive value. There is a relation.
uh,
These are different.
okay. And, okay.
No.
And model based?
And then, uh, yeah, and then you have other set of and before that, and if you have some intersection of these two, you have this actor critic based methods,
That's
which
it.
we have discussed, right? Like which uses the advantages of both these different. So that is one type of one set of algorithms. And then there are again other set of algorithms called model free and model based. So model based are nothing but you already have a model. So you have a model in the sense like you know your rewards and you know your transition probabilities.
Hello? Ah, yes.
Uh, so here, you have this things like model based model. Here, what happens is here you already know your rewards and your state transition problems or dynamics of the model is included. The state transition problem. So you are assuming that you already know or you have idea of your things. But in these model-free methods, you are assuming that you don't know this. You don't know about the R, you don't know about the P of S also. So
Acha.
we have to learn. So by interacting with your environment, you will learn this. So you have your agent here and you have your environment. So you will take some action from action and you will receive some observation. Observation is nothing but your reward. And by doing that, you will slowly understand or calculate your rewards and you will try to understand the state transition probabilities also. So most of the RL method, whatever we are discussing, learning based or learning course or action specific or almost everyone, DPG,
Hmm.
trust, GPU, EPU. So whatever the algorithms we are discussing, all these are model free only.
Model
So
free.
most of the algorithms that are there in RL are model free algorithms.
We don't give them rewards. What? We don't define rewards.
No, agent interacts with the environment and then it will give you responses.
Acha. I mean, acha. There is no rewards. Win or lose is also not a reward.
But it doesn't know the reward.
Acha.
See, in exploration and exploitation, we discuss what happens.
At last, we'll get a reward, right? Pulling a lever, then if we win, then it is a reward. If we lose, we don't.
Means if you take it in this whatever the graph diagrams we are doing, right? Here,
Uh,
what happens? You will take some state, you will take some action, and you will get some reward. So we are observing your reward. If you are exceeding them, initially you don't know your reward, but
acha.
by interacting with the environment and taking some actions, so you are getting some rewards, right?
Okay. Okay.
So you are getting some idea regarding how much reward you are getting when you take some action. So we are getting some clarity on those aspects.
Mm-hmm. Mm-hmm. Right.
Yeah. So that is called model free based learning. So model based are nothing but you have this Monte Carlo research and again you have some controllers related model based. So there are few algorithms model based also, but generally when you are doing with some control system based substringent kind of problems, we will use model based. But most of the cases we will go with model free based algorithms.
Acha.
And then yeah. Then model based is nothing. But learn the model on the MVP and then try to solve the MVP problem. Okay, model free is nothing. But learn to how to act without dependency to learn the transition problem. Yeah, we will discuss about this model free RL and yeah, we'll discuss about the DP and TP as well. So,
Mm.
but as of now, we take that. We'll discuss about the Q learning part. So Q learning is a very basic algorithm in RL, and it is an important algorithm because this Q learning concept will come almost everywhere in the further algorithms that are that we'll discuss or that are coming up of learning. So this is an important algorithm we have to know. It's a model free algorithm, so that we are clear, right?
Okay.
And then it's a tabular method. So tabular method in the sense it has some large tables which give each action value pair. So we have told that I made one table, right? So it has its state and action.
Mm.
So what similarly this Q learning tabular method is nothing but. For every q value you are calculating, you will get that action. Sorry, whatever the action is there, for action you have corresponding reward also or q value.
Hmm.
So every action you have some corresponding q value. That q value is nothing but reward.
We don't. This is a model fee, right? We don't have reward.
When we interact, we'll get right. We have it. It's
Okay.
not that we don't have, but it
Acha, acha,
doesn't
acha.
move.
Oh, okay, okay.
And then
Oh.
this is off policy. So again, you have something in the same model free model based right? You have on policy, and this in you have something called on policy and off policy.
Mm-hmm.
On policy algorithms and off policy algorithms. So on policy is nothing but it will learn with only current policy. It will only do the learning from current policy. Off policy is nothing but it will use the past experience or previous policies.
Mm-hmm.
Some previous policies are there that also it will use for updating its whatever the present policy is. So off policy algorithms are nothing right. Your Q learning is off policy basis,
Mm.
but if you take SARS is on policy. So what exactly is on policy and off policy? These things will see later.
I'm not understanding that in what is the learning in all policy? What is the we have the policy or just we are just doing it? Then what is the learning in it?
No, no. I told that we have to find the optimal policy.
Okay.
So
And
if
off.
you're
Okay, okay.
finding your optimal policy only with current policy, only by updating your current policy or
Okay. Like MDP. MDP is also an on policy.
no, no. MDP is a method which solves this type of problem.
Okay.
But if you have some RL problem, you will formulate it in MDP
Okay.
first, and
But
then if you are using SARSA kind of algorithm, it performs on policy updation.
right.
Or if you are using off policy, the Q learning kind of algorithm, then
Right.
it will perform on policy.
Okay.
Sorry, it perform on policy. So
Uh,
what is the same kind of MDP only? Same MDP problem you can solve in different ways.
okay. So, MDP problem we cannot solve in off policy, right?
No, no, same MDP problem you can solve either with off policy or on policy.
Because past we cannot in MDP we cannot have the past states, right? Past information and all.
See, current policy or past policy, past experiences are nothing but again when we discuss. So first we'll discuss what is Q learning. So I
Okay.
told the Q learning is off policy. First we'll discuss what is Q learning. Then we will discuss why it is off policy. Then we will discuss difference between off policy and on policy.
Okay.
We have this Q learning part. So this Q learning is nothing but so what it is signifying or what it is signaling. You have your it's off policy. And you will update your Q table. So that we told that you have some Q table. Right? So this Q table updation is nothing but you have your Q value. And then you have this term, right? This term is nothing but this is your target. So a target is nothing but you have some what is suppose you have your Q value. And what you are doing your Q value plus the next whatever the updation you are doing. So what is your gradient descent is doing in the sense, um, of x or something whatever the of x is x of x plus delta of f of x. So some gradient updation we are doing. So in the same way, what you are doing your Q value is nothing but your previous Q value plus alpha into this alpha is nothing but here you will have some alpha value also. This is nothing but your learning rate.
Mm-hmm.
Which we have defined. So you have this learning rate, and here what you have is you have a target. So this target is nothing but and how much like this is nothing but like your optimal Q, temporary optimal Q value. So you are calculating some Q value, which is your target or the expected maximum, and then you are doing a gradient of this with the present Q value. So this is nothing but temporal difference. So if you take a concept of temporal difference, yeah. So there is something called if you are making updation or when you are finding. So what is your aim? Aim is to find optimum policy. So how to reach the goal, reach this aim? To reach it, either you can use dynamic programming or you can use multi-worker based updations, or you can use TD, temporal difference based learning. So this TD is what we are using. So here in Q learning, we are using this TD concept. And what it does is it does this both here. So as of now, again, like in next class, we will discuss what is this dynamic programming, what is this quantum combo, and how TD is using both of that. So we will discuss all this. But as of now, you take it like this temporal difference is nothing but you have the target estimate of the region, and you are doing the gradient or difference of this target with your present value. Okay.
Target. What is the
Yeah, this is
target?
something called bootstrapping also.
Mhm.
Bootstrapping. Okay.
Target, I'm not getting. How are we getting the target?
No, target is nothing but you are calculating from your RT plus 1 is nothing but your future, whatever the reward you are getting, immediate reward, plus gamma into max of. So this is nothing but your this only, right? If
Uh,
you see,
Bellman.
yeah, yeah, wherever the calculation you are doing. Yeah, here we are seeing, right? This nothing, somewhere else. But you remember that, right?
Uh,
That this is
yeah.
when you are calculating your Q of S, then you will take this into account, right?
Uh,
Yeah, yeah. So we will calculate this, and then we will do a gradient of difference of this with the present value. So finally, what happens at the end of the day or at the, after some convergence, what will happen? This will equal to this, right? So slowly, slowly, you have some target. What you do, you have some Q value. Then you have some target. If you see what we are doing here, we have some Q equal to Q plus target minus Q equal to Q plus target minus Q with some learning rate. So as of now, take learning rate as 1. But plain, we are doing this only. So here what is happening, after some iterations, Q is approaching T. Assume that Q equal to T or it is approaching. Then what happens? This Q equal to Q plus 0. This equal to Q, right? So when T approaches 1, approaches T, then it will converge. So this algorithm will converge. So what we are doing, we are slowly, slowly bringing your Q value close to target.
If we just know the target, then what we are approaching, I didn't understand. Like we know the target
This
before.
target is nothing but this target is again changing now. Every time this target will change. So for this first update, you have this target, right? Again, whatever this R of T and maximum Q value you are calculating, everything will again change. So this target is not static; it is dynamic. Okay?
That's it.
So finally, when your Q value reaches this target, which is sort of like goes on updating, and finally this target also will converge or reach something standard or something it will reach, and finally this Q will reach this standard. When it happens, then this Q will become your Q star.
Uh,
Then whatever the policy you are going to get, it will be your 5 star. So
this,
finally we reach our aim, right?
I
This
didn't
is
like just an overview I got, but if you give an example, like some one scenario, then this is the Q value, this is the R value, this is the this value. Then again this happened. Again after next iteration, the Q value has converged to this. Like all the values, if I get, that will be great.
okay, okay. What we'll do is we'll see an example of we'll understand
Yeah,
uh,
yeah.
how it works.
Because not getting
Can
it.
you take the concept?
Because
Sorry.
if yeah, I'm not getting it. Like we already have the target, then what we are doing? Like
So it is nothing but see, that is where the temporal difference of timing programming is. So that is the reason I told like you should understand all these things. If you understand these things, then you will understand how exactly the algorithm is going to work. So I'll teach you these things. Then you'll get some clarity on what exactly we are updating or what is this target. Why you are using temporal difference. So temporal difference is a very big concept. So we'll go through that. Okay.
okay, it's very confusing. Like what's going on? I don't know.
Yeah, yeah. So that is the reason you don't think more. So as of now, you just take like whatever I'm telling, you just take it as granted. You just assume that you have some true value, and
Okay.
then you have some target value, and you are always trying to sort of take a decision between this target and the two. And when this two is approaching your starting your software updation. That means your value is content.
That I got. Okay. Okay.
Yeah, so that you understood, right?
Yeah.
So
Yeah.
as of now, you take this. So
Okay.
what is this target? Why you are doing this difference? And what is this temporal difference? That we will look into.
Okay.
Okay, and then you have this two table updation in the same way. So the same way only they have demonstrated. And then you have your Q learning versus optimal MDP. So your optimal MDP is the one which we have saw in the previous slides, right? How we can find the C sharp value.
Mm.
So this is your optimal MDP, and this is your Q learning which we can use now. And then coming to off policy. So if the agent learned the policy from the experience which was generated by other policy. So instead of current policy, if some other policies are there, and you are trying to learn from that other policies also, then it is called off policy, which we have already discussed. So why Q learning is off policy because it will learn from the experience of also. So what is experience and there is something called experience buffer or experience. So that is a very important concept which we have to see. So, what is experience typically looking at? You will store all your whatever the policies are you are running on, or when you are providing your training part or whatever episodes you are doing. Those things are stored in some buffer. And after some time, you will what you do is randomly pick a batch of that, and you will train this agent again on that. So it is like instead of training on the current policy, you have stored some other policies also somewhere, and then you are taking them and then training the policy on those experiences only. So the advantage of this is you are reusing the policies, right? You have stored the policies there, and then you are updating or using them. So it is sample efficient. Of policy sample efficient.
Okay.
That is one advantage of policy. And then yeah, so this is the same equation what we saw. And then on policy is nothing but the policy, the agent only learns the policy from the experience which was generated by current policy. So if the experience is not generated by current policy, the learning won't happen. So I don't know what you understood. On policy is nothing but we have some means it learns only from current policy. Off policy is nothing but it takes the experiences of other policies also and learns from other policies also.
Other policies means once can you repeat?
It past policy, whatever the past previous policies
So
it has been going through, or whatever the policies it has been executing, or it has been using.
can you go to the previous slide? Here also it's saying experience, right? The agent can only learn the policies from the experience. So this is also past experience on policies saying.
No, no, which was generated by current policy.
So off policies also doing from experience, on policies also doing from experience.
No, no, no. This is like the agent can only learn the policy from the experience which was generated by current policy.
Huh.
Okay, so on policy means only with current policy. It will run.
What is the other policy then? Where is that other policy coming
Off
from?
policy is nothing but it learns from it was generated by other policies. Now, the past policies will be there, right?
Okay.
See, a policy is nothing but see what you will do in the case and in the case what happens. You have some you have some first thing what is episode? What is episode is nothing
Epoch.
sort of. So when we are reaching your terminal state, your it is a finite horizon MDT, MDT. Then when it reaches your terminal state, you are ending your it is one episode. So when you are reaching, it is one episode. So when this unepisode completes, your one policy is completed, right? One time you want suppose you started with some arbitrary policy and you have completed one episode. Then it is your first policy P1, and then you have did some improvement in the policy based on this value attraction policy adjustment something. You have did some improvement, and then you have chosen the second policy in the second episode
Mm-hmm.
P2, and you are using this P3 as your third policy, third policy in the third episode.
Okay.
And now you have this P4, and this is your current policy. So this is your current policy, and this is your past policies. Okay.
What is experience in that thing? They were saying
Yeah.
experience.
So what you will do these things, you will store in an experience video buffer. You are storing it here.
Okay.
And then what you are doing, you are taking this buffer, and then you are randomly sampling, randomly you are picking some batch, picking some batch, and then you are updating or you are using your agent this policy, whatever the policy updation. So you are using this is your current policy updation. This is off policy.
Okay. But the previous policies were bad. That's why only we went for P4, right? Why are we taking experience on the bad policies?
Why we are taking because when you are means we are not taking it directly, right? We are sampling
Mm-hmm.
a random batch from it, and when we are doing it, we are using that in our current policy updation. So how much we are using it, we don't know it.
Ah, yeah.
Suppose how much percentage or how much you are using. First thing is you are doing aggregate of this data, and you are randomly sampling it. So why you are randomly sampling? Why you are taking aggregation? Why you are updating this here? What is the advantage of using this here? Again, if you do a discussion on off policy versus on policy, discussion sort of.
Okay.
Okay, which one is better? Why we are going for this? Why we are going for this? All these things again. So if you see this one, this is computationally expensive, and but it's sample efficient. This is easy to execute, but sample complexity is high. Sample complexity is nothing but number of episodes it need to learn a particular task or find some optimal policy. Oh, why? Because this is only learning on the current policy, right? Because of that, how many times you are going through or whatever the number of episodes you have to run, it is more. So episodes are more for this. And for these episodes are less. So it's like that. So we will discuss on when we discuss about this. We discuss about how exactly this off policy, non policy, before, and which one to use when. We'll discuss. Okay. So there are two discussions we have to do. One is off policy versus on policy, and one more is model based versus model. If you use optimal policy at times, most of the key table won't be updated. You will find the policy not optimal. Yeah, yeah. So when we are using this off policy updation, what we will do? we have to know about the rewards also. What are the rewards we are going to obtain? Then we are starting with some arbitrary Q value, and then we are updating your Q value. That is what we'll do in our Q learning piece. For that, we have to do some exploration and exploitation. Then only we will know
Hmm.
which action is giving you which Q value and that is the method. So we should know about the Q value part.
Right.
Yeah. So here again it is like this is why we are doing this exploration and exploitation. Especially why we are doing this because this is a model. What we say, this is a model field.
Hmm.
That is the reason we are going for exploration versus exploitation.
Correct.
So here it is like so here what happened. You have this model based is there. Here, what happened? Already you know your rewards. What is the reward for corresponding action? You know your constant problem, everything. You know. Then why you will do? Means everything is fine, right? You will do planning. This is called planning. And in model field, you don't know these things. So if you don't know these rewards and transfer probabilities, what you will do? You will do this exploration and exploitation. Now this is okay, right? Now you
Hmm.
people are able to understand, right? When we why we will use model based and why we will use model based,
Hmm. Right.
and why you are doing this exploration and exploitation.
Yeah, yeah. That is all. Model free, we don't have the rewards. That's why we are doing exploration and all.
Yeah. So this Monte Carlo research is a model based. Why? Because
Yes.
what happened? You have your rewards. If you know your reward, then whatever you are doing is a research kind of. So we are just doing a planning of suppose there are some 10 possibilities. So which possibilities if you go, how much reward you will get, or what is the reward that you are accumulating. So it is just doing a research kind of algorithm and then proceeding from. So we are doing the planning here.
Hmm.
So in Go game and these things, they use this Monte Carlo research.
Monte Carlo. How? We will not know the reward for every state, right?
If you know it, as of now, you take it like if you know it, if it is a model based or if you know this, then you will go with the model based research.
But AlphaGo has like millions of states. How can we know all the states and rewards?
No, forget about AlphaGo and other things.
Okay.
So as of now, we know that model based and model based. These are the things.
Okay.
So and Q learning is what it's a model free. It's a model free method, right?
Yes. Yes.
Yeah. So, means if you see, again there are some discussions like just Google like why tool learning is model filter.
Hmm.
So again there are a lot of discussions arguments and it will come against so this field. So for everything there's a lot of theory. There are it is very in-depth understanding that has to be. But as
Hmm.
of now you take things like okay whatever I'm doing just research.
Hmm.
So you have this exploration versus exploitation dilemma, and then you are doing this epsilon theory. You are two learning is using the epsilon theory strategy. So you already know what is the epsilon theory strategy. We have
Hmm.
discussed in the
Right.
basic mathematics.
Yeah.
So 1 minus epsilon times it will exploit and epsilon times it will exploit.
Hmm.
So this is clear, right?
Yeah. Yeah. I mean upper level only, not.
Yeah, yeah. This is like this thing we have already
Ah, no,
discussed.
no. This thing is clear. Like till now, you said right. Till now.
Yeah, yeah. So yeah, so Q learning is nothing but it's off policy 3D control algorithm. So it is using off policy and you see it is using temporal difference also. So temporal difference is what we have understood, right? When we
Uh,
are doing the difference of the target and the key value and
mm,
we are doing the updation, right? I told that that is called the temporal difference part.
mm,
Okay. So the algorithm for Q learning is nothing but you are initializing your Q value arbitrarily. And for two terminal state, if it reaches the terminal state, it is over only. So what you are doing, you are initializing the status. and then you have some sort of like you are taking action using a particular policy which is derived from your QL. So what you will do here, first you will use your epsilon greedy method to find the QL, and then you will take a action. You will derive one policy from that, and you will take an action from this particular policy that you have derived. And once you take this action, so you have your agent and you have your reward. So you are taking some action. So you have taken some action and you are observing your reward, and you are going to some next status dash. Then after doing that, what you are doing, your update. So you have means you have some key value, q of sa, and then you have performed some action, and then now what you are doing, you are updating your key value. So whatever the previous key values there, you are adding some gradient or some additional term to it, and then you are proceeding to next stage, and you are repeating the same. So iteratively, what you are doing, you are updating your key value iteratively. So again, you are using this key value here, and then you are getting your action. And then from the action, whatever the observation you are getting, you are updating your key value again. So slowly, you are step by step, you are updating your key value. After how much time you will update your key value? When this key value reaches your target value, this key value will convert. So up to that time, we will run this application. Okay, this many episodes we will run. Okay.
Hmm. Hmm.
So up to this point, you have got some idea of what exactly this tool learning is, what are these model free and model based methods are, and what are these off policy and on policy methods are. So people are able to understand most of
Oh,
things, right?
yeah, only the definitions. Like,
Yeah, yeah. You just take it as it's in this file because it's 3 months course, right? So in RLS, it will take some lot of time to understand. So I'm just telling you on the top so that you will understand some basic things of what is what. And then
hmm.
if we discuss further, or if you are go deeper, if you go deeper, then you will clearly understand like what exactly this on policy is, what exactly the off policy is, which type of applications use which type of policy based on why we should use it. So all these things will be there.
But now I cannot put reinforcement learning in my resume, right? Like it
Yeah, yeah,
doesn't.
yeah,
Yeah.
10 plus is over. So, so we will
Yeah.
slowly
Okay.
understand this.
Right. Right. Okay.
Yeah, yeah. So we will most probably will have class today night, and
Ah.
I'll cover other things also, and we'll see.
Okay. Okay.
Okay, sure, sure. Okay, bye.
Okay. Bye.
Okay. Just to read up the things. Whatever the things are there, you are noting down.
Yeah. Yeah. Yeah, I'm
What
noting
are
it
the
down.
things? Or
Mhm.
actually, in that introduction to RL, right, just read that book. You'll understand the things.
Oh,
So if
that.
you see, like they in that book, they will tell that even the brain and the neurons, what are the human brain or whatever animal brain and everything, they will learn using this TDM, temporal difference.
Acha. Uh-huh.
So yeah, so you just learn that book. Read the book and then tell me these things.
Mm. Okay.
Uh,
I mean, I'm not a book guy, so I'm not reading at all. Yogesh is reading a bit.
you should read it because like it's important. Like along with what I'm telling, you should parallelly read books also. Then you will understand and able to follow the class.
Or maybe some MIT or what
Videos.
NPTL videos, something.
Actually, there is one person, Balaraman. One Balaraman, one professor is there. So
Uh-huh.
he will.
Balaram.
Yeah, Madras,
That's
IIT
IIT
Madras.
Madras.
I guess
Yeah, yeah.
Yogesh is
Just look
following that.
into his. Yeah, just look into his few
Uh-huh.
classes.
Okay, okay.
Yeah, it will be good. If you
Okay.
want to go to classes, or else if you want to look into standard classes, then you look into this videos. I'll just send a playlist. I'll send
Yeah, yeah. I am a video guy only, so
okay, okay. I'll send this list.
okay.
Book is also good. That having some deep understanding with the book.
Yeah, yeah. Introduction to RL is very standard
Yes,
book. So anybody coming to RL or something, they have to read that. So no problem at all. Okay.
yes, yes.
Okay. Bye bye.
Okay. Bye.